latest implementation of Phillips's numerical lifting line algorithm. I'd be biased if I said it was the best because I was the one who wrote it, but I'll leave that up to your judgment then. MachUp X is hosted here on GitHub. If you go to GitHub, you can just search MachUp X and you'll find this repository page. If you're not already familiar with GitHub and with Git version control, I highly recommend either reading a tutorial on it or something like that. It's an incredibly useful tool, and will be very valuable to you throughout your career, not just in school, I would say. So I recommend looking into that, and that'll help you with using MachUp X. All of the documentation to MachUp X is found at this link here. It's hosted on Read the Docs. This tells you about MachUp X, how to install it, where to get the source code from, how you could interface with MachUp X, how you're going to create input files, the class methods that are available to you, and then there are some notes on there that I've kept for future developers. That is something that we recommend using MachUp X because of. We will be continuously developing this one, so there will be bug fixes, there will be new improvements coming out, and even within the next couple months, we're going to be, I'm working on updating it right now to include some corrections that improve the accuracy and ensure convergence for swept wings. So watch out for that. I highly recommend, if you've got questions about it, everything's here in the documentation. It's laid out pretty thoroughly. If there's things that you can't find in the documentation, then get a hold of us, and we can add it in there because we want it to be as thorough as possible. I'll talk about how to install MachUp X. All these instructions are, again, it's on the documentation. What I recommend is learning how to use Git, getting Git installed on your computer, and cloning this repository. All that means is you tell the Git software to take all of the code, the files that are on this remote repository, and download them onto your computer, create an exact copy. You do that using this URL here. If you don't want to use Git, if you're not comfortable with that, you can just download a zip file that contains all the code. You extract it onto your computer, and you're ready to go. Once you have the code downloaded, it does need to be installed. So Python is a scripted language, so you're not building the code, you're not compiling it or anything, but it does need to be installed. So what you do is you go into, I guess I need to pull up another command prompt here. From your command prompt or your terminal, whatever you're using, you go into wherever you extracted or cloned the MachUp X source code. So for me, that's git-repos/MachUp X. You can see this is an exact copy of what's in the repository, and then you type the command pip install dot. Dot just tells it to install the current folder. Hit enter, and that'll chew on that for a second, and it should spit out that everything's okay. If you're like me and you make changes to the source code, sometimes people want to see things that are printing out immediately. Anytime you change anything to the source code, you do need to reinstall it before those changes will be accessible to you. Okay, so you can see it said successfully installed MachUp X. You test the installation using the command py.test. If you're on Windows, that's py.test.exe. What this does is just runs a whole bunch of unit tests that we've written, and this makes sure that your installation of MachUp X is functioning properly, it's producing the correct results, and there aren't any bugs with how it's working on your system. So I'm just going to go ahead and cancel this because I know it works on my system. We won't worry about that. But again, if you didn't follow that or you're not sure how to do it, there's step-by-step instructions. You here on the documentation, hit source code, cloning, installing, testing, everything, it's all there. So now I'm going to talk to you guys about the input file structure to MachUp X. If you're at all familiar with MachUp, you know that up till now there's just been a single input file. We changed things a little bit with MachUp X because MachUp X has the capability to analyze multiple aircraft at once. So you can analyze the aerodynamics of an aerial refueling or like drones in swarming flight. You can get that kind of analysis going. So whenever you create or start working on an analysis with MachUp X, there's two input files that you're dealing with. One is a scene object. That's this scene.json I have here. The scene object tells MachUp X about the solver, how you want it to solve the lifting line algorithm. It tells it about the atmosphere that the aircraft exists in, so density, viscosity, wind, that kind of thing. And then it lists the aircraft and where they are in the scene. All of the information for the input files is on the documentation. If you go to input files here, this talks about JSON format. You can specify different units in MachUp X, and it will automatically do conversions for you as long as it recognizes it. And then it goes through and describes all of the objects that need to exist in the input file. So you can find everything that you can ever want there. Anyway, in the scene input file, tag is just an optional tag telling you, it's a note for you to remember, hey, this is what this specific file is for. Solver contains parameters that tells it how to solve the lifting line algorithm. I would recommend using the nonlinear solver. The linear solver just makes a few assumptions, small angle approximation, removes nonlinear terms, and it's generally accurate for wings of high aspect ratio at low angles of attack. But the nonlinear solution takes that and it refines that down a little bit. So I recommend sticking with nonlinear. It's not much slower. The lifting line algorithm is very fast anyway. You can specify the units that you want, or the unit system you want, whether it's English or SI, and that determines what your default units are. Then within the scene, this is describing the atmosphere in the aircraft. First query is the atmosphere, where you tell it all about the density, viscosity, and stuff like that. I understand for your guys' project, you need to do your analysis at Logan elevation. MachUp X does have the capability to do a standard atmosphere profile, and then you can put your aircraft at that altitude. I recommend not doing that though. What I would recommend doing is setting the density to what you want and then leaving the altitude in the state of the aircraft just at 0. That will increase the numerical accuracy. That's an issue that I have with MachUp X that I'd like to fix in the future, but that's beyond the scope of this. So anyway, I would recommend set the density to what you want rather than using the altitude to set the density. And then here's where you list all the aircraft that you want in the scene. You guys will just have one aircraft in there. You give the name of your aircraft. That's arbitrary. I've decided to name this one Goat Glider. And then you give the file path to the JSON object that describes your aircraft. I'll go over that in just a second once we're done with the scene. And then you need to tell MachUp X what the state of your aircraft is. Currently, MachUp X wants to know the type of state you're specifying, whether you're specifying an aerodynamic state or a rigid body state. Really, the only difference between the two is how velocity is determined. If you're telling it you're specifying an aerodynamic state, then you can give it a velocity magnitude and alpha and beta, or you can give it u, v, and w as a vector. If you specify that you want your state type to be rigid body, then you have to give velocity in Earth fixed coordinates. I recommend you guys will want to just stick with aerodynamic type and probably just give it velocity and alpha and beta. And these are all in the default units. The default units are listed in or on the documentation, but default for velocity is feet per second, and alpha and beta default to degrees. So that's pretty straightforward. So this file tag right here tells MachUp X where to find the file that's describing the aircraft. So that's this file here. This describes all of your geometry, your airfoils, section properties, some of the mass properties, reference areas, and that kind of stuff for the aircraft. First thing you put in is you give it what your center of gravity location is. You give it the weight of the aircraft. This reference dictionary or object, this tells you, or this tells MachUp what reference areas and lengths you want for non-dimensionalizing force and moment coefficients. That's all optional. It will MachUp X will calculate that for you if you'd like. But this, you can be more explicit about it and make sure you know exactly what's going on. This next object here, you give it, this is sort of an airfoil database that it will pull from. So you tell it the names of airfoils, of all the ones that you want, and you give the linearized model for that airfoil. As well as you guys need to export a STL of your aircraft or of your glider. And so you need to explicitly tell it the geometry of the airfoil, in which case this is just a NACA airfoil, so you can give it the key NACA and tell it what the NACA designation is. And MachUp X is aware of the NACA equations, and it'll generate that geometry for you. But you just need to make sure to include that. If you don't, it'll get mad at you when you try and export an STL. But these airfoils get pulled from later on as you're specifying wing segments, and I'll go over that in just a moment. This next object is where you list all of the wings that are on your aircraft. And this is actually wing segments. So MachUp X is really flexible with how you can define wing geometries. You can create really weird nonlinear distributions however you like. It doesn't care. But if you'd like to create, if you'd like to have a center section and then stack more sections onto the outside of that, then those would be separate wings in this dictionary. I've created a really simple one right now. All it has is a main wing, a horizontal stabilizer, and a vertical stabilizer. For each wing, you give it an ID number so that other wings will reference your wing. You tell it which side it's on, tell it if it's part of the main wing. That's for determining reference areas and lengths. All of that is based off the main wing. You give it the semi-span. Here's where you tell it the airfoil. And this points back up to these airfoils that we defined earlier here. So if you ask for an airfoil here that you didn't define up here, MachUp's going to get mad at you. So don't do that. You can give the chord, the dihedral, the sweep of the airfoil, and these can all be functions of span. This is described in the documentation, so I won't go over it in depth. But you can give the chord as a function of span. You can give dihedral as a function of span. You can give sweep as a function of span. So you can make crescent wings. You can make all sorts of different shapes, however you like, as long as you can figure out how to specify it using a distribution. Grid that tells it how to set up the lifting line equations for this wing segment. All you really need to be concerned about is this is the number of grid points. It defaults to 40. If you want it to be a little more accurate, then you can bump that up, but 40 is a pretty good number. And that's grid points per semi-span. It also automatically defaults to cosine clustering, because that's shown to be a lot better from what Phillips has found out. So you don't need to worry about that. This is my horizontal stabilizer. The only thing that's different here is it has a connect to object. this is telling it how you want its position defined. So we didn't specify that for the main wing, so the mockup is assuming that the root quarter chord of the main wing lies at the aircraft origin. If you don't say anything, that's what it assumes. Here, though, we want to put the horizontal stabilizer at the back of the plane, so we say connect to, this is the ID of the wing that we want to define it relative to, so we're saying define the horizontal stabilizer relative to the main wing, that has ID 1, so relative to the main wing, relative to the root of the main wing, and I want it 5 feet back from the main wing on the x-axis. So that's all that is. You can also ask it to do location tip. So again, if you wanted to add on winglets or another wing section to the main wing, you could say location is tip, and then don't put anything for any of the offsets, and it will automatically take those 2 wing segments and put them on at the tips of the main wing. This we've defined using a different airfoil than ACLA 0010, as opposed to 2410 we have above. For the vertical stabilizer, of course, we only have one, so I've just arbitrarily said that I want this to only be on the left side, and I've given it a 90-degree dihedral. That's how you would do a vertical wing segment. And again, this like the horizontal stabilizer, I've said define it relative to wing 1, the location or the root of wing 1, and I want it 5 feet back from that. So that's about it for input files. Like I said, these are all explained in the documentation. There's a lot more capability, especially for defining nonlinear geometries and non-constant geometries than what I've talked about here. So I recommend going to the documentation, giving that all a quick read through, just so you understand what MachUp X is capable of as far as defining an aircraft geometry goes. Now let's talk about how to script MachUp X in Python. If any of you are familiar with MachUp Pro, the Fortran version, you know that you need to run that through the terminal. MachUp X, you can do both. I'll start with talking about scripting it in Python, just because I think that that's a lot more powerful for analysis. You can have everything all in one script and run as many times as you want. You don't have to deal with any kind of output files, but I will briefly go over how to run it through the terminal. So the first thing you have to do is you have to tell, you have to give it the input file and pass that as the argument to this scene class, and that gives you a scene object that you then call all of your functions on. I will say right here that instead of giving it an input file, you can take these input files and store them as Python dictionaries in your script, and you can pass those to MachUp X instead. Depending on what you want to do, that may be advantageous, and I'll talk about in just a second why that might be advantageous for you. But that way you can have Python automatically make changes to your inputs without having to worry about writing it to a file and reading that file back in. You can just keep it all in your script as a dictionary. Once you have it read in, I'm going to talk about you can set the state. That's this here. So again, you just specify the state dictionary just like it was in this scene object. Here I just want to give it a velocity of 15 feet per second. I don't want alpha or beta, so I've left those blank, and MachUp X says that those default to 0. And I'm going to ask it to set the aircraft state to that. So I give the state is equal to state, and the aircraft name. I do have to specify the name of the aircraft that I'm wanting to set the state of. Since MachUp X can handle multiple aircraft at once, you do need to tell it explicitly which aircraft you're wanting to do this to. Otherwise, it just says, I don't want to decide which aircraft you're trying to intend. This aircraft name is the one that you've given here. So see, I've called it Goat Glider here. So I'm telling aircraft name is equal to Goat Glider. Once you've set your desired state, and I've just pulled this up to show you how to do this. When you input this scene, it'll automatically put your aircraft at this state. So I've brought in the scene, it set the aircraft to this state, and then I just immediately changed it to another state. So that's kind of pointless on my part, but I just wanted to show you how to go about doing that. Once you import it, you can call this lovely function to display the wireframe. What that does, and my terminal's doing weird things. What that does is just show you a wireframe of your aircraft in the scene. So it gives you a general idea of what the geometry is, and it's just a Python graph. You can see that here. It gives you a general idea of the geometry, so if you're a visual guy like me, you can get a better idea of what's going on. The blue dashed lines are the horseshoe vortices that it's using for the numerical lifting line computation. I like seeing those. If you don't like seeing those, you can turn that off. That's just a parameter to display wireframe. And so that doesn't have to be there, but you can see this is the glider I've defined. It's got a little bit of sweep, a little bit of dihedral. There's the empennage back there. And that's all that I've asked for at this point. Before I go much farther, I do want to say all of these functions that I'm calling on my scene, those are described in the documentation. If you go to this scene class, this tells you all the functions that you have available. You can add aircraft, get the aircraft aerodynamic center, aircraft control derivatives, aircraft mean aerodynamic chord, aircraft stability derivatives, display wireframe. That's the one we just had. This is all in the documentation. So if you're ever curious what you can do with your scene class, just come look at this page. So now we actually want to, calculate some aerodynamics here. So let's get the forces. So all you have to do is call myScene.solveForces. This solves the lifting line algorithm based on the parameters you specified. And it returns a dictionary that contains all of the forces and moments acting on the aircraft. Again, since MachUp X handles multiple aircraft, it will give you back the forces and moments acting on all aircraft in this dictionary. So what I've done is I've said I just want the forces from Goat Glider. This JSON.dumpS function, that's just a function that I like to use that formats a Python dictionary nicely when you output it to the terminal. So I'll show you what that does. Oh, I just need to save that. There's our wireframe. I'm going to comment that out because I don't want to keep seeing that. Okay, so this is the output from lifting iron algorithm. As you can see, there's a lot. And that's because MachUp calculates your inviscid forces, it calculates your viscous forces, and it calculates your total forces. MachUp X is also capable of doing both dimensional and non-dimensional analysis. And by default, it does both. If you don't want that, we can just go in here and say dimensional equals false. And that's saying I don't want the dimensional data, I just want non-dimensional stuff. We can go ahead and rerun that. And you can see now we just have coefficients coming out. But still, I don't really care about it broken up by, so this is it broken up by wing segment and by whether it's viscid or inviscid. So rather than having all that, I'm just going to ask for the total. And I do that just by indexing once more on that dictionary. And now you can see that all it outputs is my total aerodynamic coefficients for the aircraft I'm concerned with. So that makes things a little more convenient. As you can see, I've clearly not designed this glider very well. At a 0-degree angle of attack, we still have a negative pitching moment. That means my center of gravity is off. So I can go back into the glider and I'll shift my I'll shift my center of gravity back. So I'll put it at negative 2.25 feet. Let's try running that again. Yeah, I've managed to decrease my pitching moment, but it's still there, so I'd need to move the CG back a bit further. This is the exact kind of thing where I was saying it might be advantageous for you to have your input as a dictionary in Python. If you do that, then you could set up some kind of while loop and do an iterative solver, like a secant method or something, to position the CG such that it drives your pitching moment to 0 at your 0-degree angle attack, if that's what you're going for. That's just an idea. So that would be a way to use the dictionary input advantageously here. Okay, so not only do you want to know about the forces acting on the aircraft, but you want to know about its stability, of course. That's the whole point of this first project. So you do that by calling the aircraft derivatives function on your scene. And then again, this will just print out the derivatives for Goat Glider. And let's see how we do. Derivative solver takes a lot longer to solve just because it's doing central differencing. So it has to solve a whole bunch of different points. So these are our forces, and these are our derivatives. You can see they're sorted into stability, damping, and control derivatives. Now, of course, for our glider, we didn't specify any kind of control surfaces, so I didn't go over that in the input files. But that dictionary will be blank when you output your derivatives, so don't worry about that. That's just what it's supposed to be. But we can see here we've got a negative pitch stability derivative, so that's good. We've got negative roll stability derivative, that's good. And we've got positive yaw stability derivative. So we're actually doing pretty all right on this glider so far. And then what you guys are going to have to do is you need to get your geometry into SolidWorks so you can create a model as well as getting your mass information. We've come up with quite a few ways of getting geometry from MachUp into SolidWorks. And as Ben can tell us, they are not all created equal. The two useful functions for you guys, I would say, is export STL. This takes your aircraft and creates an STL of it. If you're not familiar with STL, STL is just a shell model of your geometry. Some people joke that it stands for Standard Triangle Language, which is basically what it is. It turns your surface into a whole bunch of triangles, and I'll show you what that looks like in a bit. You can also export DXF files of each of your lifting surfaces, your wing segments. What that will do is a DXF file can describe splines in space. And I have to credit Ben was the one who came up with this one. And you can import those splines into SolidWorks and loft between them and get a nice solid body out of that. But again, let's just run this. It'll get my forces, get my derivatives, and then you can see, well, where's my STL? Well, it's right there, goatglider.stl, as well as here are all the DXF files. So if we open up, this is the STL. We'll open this up in Microsoft's print program, and that's the STL of our aircraft. That's funny, it looks like I've defined the wrong NACA section on those ones. Oh well. So that's what an STL looks like. As you can see, it leaves the wing tips open, as well as there's some weird interference things here. So STL might not be the best option for you to get it into SolidWorks. DXF files might be better. I don't have SolidWorks on my computer, but it's a really simple process to get a DXF file in. There's tutorials online for how to do it. It's really just a few button clicks, and voila, you have your curves. in SolidWorks, and you can just select them and loft between them. It's a pretty slick process. So I said that that's everything I want to go over as far as specific functionality of MachUp X and the things that it can do. I do want to make a quick comment that you can run MachUp X from the terminal. The way you do that is Python has this command. If you type Python -m and then MachUp X and your input file, so scene.json, that asks MachUp X to run that file from the terminal. This is our lovely logo. As you can see, it's looking for a key in the input that called run. I haven't included that because I was just scripting with Python, but if you do want to run from the terminal, you need to include run. You need to include this run parameter in which you tell it, okay, I want the forces, and I want my arrow derivatives. And this will act just as if you had asked it for those in a Python script. So you can see it's calculating the aerodynamic forces. This is just some convergence information on the nonlinear solver. And then it calculated the aerodynamic derivatives. And now it will store all of those in files. So you can see we get scene derivatives.json and scene forces.json. If I just open that up, so if I open up the forces file, you can see it's exactly the same as it was what it was outputting before. Goat glider, it's got the inviscid coefficients, inviscid forces, viscous coefficients, viscous forces, and then the totals at the bottom. So you can do that as well. I don't ever run MachUp X through the terminal unless I have to, just because I really don't like having to write to files and read from files and all that stuff. If you just run it from a Python script, then everything's in your script. You can manipulate it as dictionaries, and you don't have to deal with all this reading, writing business that I find somewhat laborious. Okay, and that's basically it as far as MachUp X goes. There's a lot more functionality that I haven't gone over. You can calculate your aerodynamic center using MachUp X. Oh, I would like to say real quick, with this set state, this would be how you could do some kind of like an alpha sweep. So if you want to say for alpha in, and we'll just do a in space from -50 to 15, and I want 30 points in my sweep. Then all you would have to do is here say alpha, and then have it be the value that you're looping through. And then on each iteration of that loop, it's set at that value of alpha, and then you could call, my scene.solve forces, and you could store those, and you could get your drag puller out of that, whatever you like. So that's the other real big advantage to running it in a Python script, is you can do alpha sweeps and beta sweeps really easily just using a for loop. That's everything that I had. Are there any questions from anybody who's listening?
I didn't see any comments online. I think this has been really good, Corey. Thanks for taking the time to go over this.
Of course.
So I'll post this. Yeah, go ahead.
Anything you feel I missed or that might be valuable for the class?
No, I think the basics of what you covered, I think that's that basically covers what they need to be able to do.
Okay. Ben just asked a question. You said, does the DXF write multiple files? And yes, it does. So calling this export aircraft DXF, that gives you one file for each wing segment, which you need to be aware if you've specified your wing segments both sides, then MachUp X for all time after that treats that as two wing segments. So my main wing, it treats as main left, you can see there, and main right, and it will export a DXF file for each. We got an okay from Ben. Cool.
Okay. Okay, well, I think that's good. Thank you. I have recorded this, and I will post it on the course website, so everyone will have access to it. And again, thank Corey for taking this time, and we'll sign off.
No problem. Happy to help out.
Okay. Okay, I just wanted to cut that video for a second. Are you still there, Corey?
Yep, I'm still there.
Okay, I have some thoughts real quick. Can you share your screen again?
Yeah. Okay.
Okay, just a second here. Actually, I'm gonna have to call you back. So
Okay.
yeah, I'll just give you a call in a minute. Okay, thanks, Corey.
Yep, no problem.
See ya.
Bye.